Welcome back to ECE 320A. You have a couple of assignments due preceding exam number 3. Exam number 3 is a little bit more than a week away, not much. And homework 3 will be S-plane, circuit analysis, convolution, and some transfer function material. That's what homework 3 is. There is convolution supplements, and if you're just now waking up and realizing there is no school tomorrow, just to let you know, we will see each other again on Thursday, but I just about forgot about that and was suggesting my next class on Wednesday that I would look forward to seeing them. Not happening. Today what I want to do is pick up where we left off last time, which was dealing with transfer functions, both active and passive. I will start talking about system response and S-plane design, hopefully after that, and then we will get into material from section 13.7, which is sinusoidal steady-state response. You can compute that without finding the complete solution. That's the idea behind that. How do we now plug in particular numbers, particular frequencies into the transfer function and find how our system will respond to sinusoidal signals? And we'll be able to compute that h of j omega graphically. We eventually will be able to do it from a Bode plot. We'll be able to sketch the Bode plot, and then you'll have it for all frequencies, and you can do it numerically with your calculator. This is now just a review of what you've already seen, but now we can talk about this block diagram description of system behavior or system analysis. And this system does not have to be a circuit. It could be an automobile. It could be an airplane. It could be a home where maybe it's now the temperature control system, and you're now trying to manipulate that or adjust that or understand how that system behaves for given input signals or input waveforms. We can find that in the frequency domain by multiplying the transforms of the system H and the input X, or we can find that output in the time domain via convolution, where we are now convolving the impulse response, h of t, to the input's waveform, x of t. Last time, I believe we looked at a couple of different circuits. This is a passive circuit. If somebody now in an interview, I hope you can remember this until you retire, if they now, and that's maybe what, in 2060? Okay, so if you're successful, you can retire in January of next year, even before you graduate with your degree, which, congratulations. Let's meet, come to my office hours, or we'll set up an individual meeting and I'll understand or learn your secrets. The lottery, yeah. But here is a low-pass filter. You can put that or sketch that, and you can immediately, by a voltage divider using impedances, like you've used resistors in the past, you can now find the transfer function either in the third formula or the fourth formula. And how do we refer to those two descriptions? The one closest to h sub 1 of s, how do we refer to that transfer function? What form is it in? Do you remember the terminology we use? That's the pole zero form, because you can immediately or very directly see where the poles and zeros are located, those values of s where that vanishes in the numerator or denominator for zeros or poles. And the other, the one on the far right, is the time constant form. The time constant is this product of R times C. That's a first order low pass, and it's passive. We derived very quickly this relationship for an active circuit. The active now, I'm not showing you how this is now powered, but you obviously have to power this op amp in order to make it work. Once you have energized the op amp, now it behaves. If you have negative feedback, it behaves in nice ways. And this particular circuit simply is looking at scaling the input by this ratio of resistors, R sub F over R sub 1. And this one actually inverts that signal, which may not be a big deal if you're just worrying about sinusoidal inputs. It's just now 180 degrees away, but you're now scaling, either attenuating or amplifying, depending on how you've selected R sub F and R sub I. The way that we have computed that transfer function might be helpful for many, many different circuits, and in particular, what if we bump it up a notch? This one, how does that transfer function change, or how does it vary with frequency? If I put in a sinusoid of 20 hertz and somebody else puts in a sinusoid of 1,000 hertz, how does the magnitude and phase, how is that influenced by this system? Pardon? So it's not a function of frequency, is it? There's no S in that transfer function. This is just a gain. So you put in a signal and instantaneously you see how that is impacted on the output by just this gain, this inversion that is now gained, and the gain could be less than 1 depending on what R sub F and R sub 1 are. Is that clear? We can't just go through life in constant mode, can we? That might be a little boring. You might not make it through retirement because you need to be doing more with signals than just scaling them. You want to shape them. You want to filter them. That means we need to put in some devices that maybe have a slightly different or a more involved voltage current relationship. Here we just have this direct connect, or this direct proportionality between voltage and current. The only thing now that I've done is placed in parallel with that R sub F, that feedback resistor, as a capacitor. Obviously, I've entitled this as a circuit that's a low-pass filter. It's active because we're dealing with an op amp. But how do we demonstrate or determine the transfer function between this input V sub I and the output V sub O? Or what's sort of the thought process, and what I'm wanting you to start seeing when you look at this circuit versus this circuit, they look very similar. You see that. All that we've really changed is we now have this frequency-dependent impedance in the feedback path. We've placed a capacitor in there. Meaning, if somebody just sketched or said, oh, here's some impedance in the feedback path, we could say this is Z sub F. Now we have exactly the same structure that we had in circuit 2, where we had R sub F and R sub 1, except now we have Z sub F and R sub 1. Yes? Question was, why do we use capacitors and not inductors? Inductors are heavy, so if you think about a space application or they're more expensive. You can incorporate capacitors onto an integrated circuit. You can build those in much more effectively than an inductor. If you need an inductor, a lot of times what you do is you actually cook one up by R's, C's, and active elements on your circuit board. You don't want to put this big piece of wire that's wrapped around the core all around in your circuit. So you can effectively do the same things with R's and C's, and that then makes it cleaner. One, it's probably much less expensive. It's much less massive in terms of weight if you were worrying about weight issues, and you can accomplish similar features. So that's why you're always seeing these C's and not any L's, but in this class I might throw L's around. In a real world application, you probably don't want to be using L's as liberally as you might want to use C's. Don't really put L's on an integrated circuit. You can put C's. Now, and that's C for capacitor, not C with water. C to shining C. This is, never mind. Wanted to make sure we were clear on that. This is now, these are capacitors that we're talking about. What is Z sub F? That was a very vague question, so you could answer it with a very vague answer. It's an impedance. It is, isn't it? But what is that impedance? Can you calculate that, or can you tell me what it is? That's just a parallel combination of two passive elements. And the two passive elements are R sub F, which is in parallel with a capacitor, and we could treat that as S domain circuit, which is 1 over SC. That's the impedance expression for that capacitor. And if you remember how to compute R's in parallel, you can do the same thing for these devices. You now have the product of the two impedances over their sum. And if we put everything over the same denominator in the numerator and the denominator, we can cancel those, and we end up with R sub F over S R sub F C plus 1. And now that can go into the same location that maybe our R sub F went into in the second circuit that we had before. The equations are still the same. Our analysis still works the same. It's just now that that impedance in the feedback path is frequency dependent, it's a little bit more complicated than just a resistor. But at low frequencies, what does Z sub F look like? What's a low frequency? DC, or 0. If you plugged in S equal to 0, what's Z sub F? R sub F. It's a pure resistor. But what happens as the frequency increases? What happens to that impedance? The denominator grows, and so this now starts to tail off or roll off as the frequency increases. You now have a frequency-dependent resistance in the feedback path. And that's why we put that capacitor there. We wanted to shape the behavior of our circuit a little differently. But now we can say that this ratio of the output to the input, which is structurally, I hope you can see that this configuration looks just like that, except that the R sub F now has been generalized to Z sub F. And you derived last time, or we derived, that that's just the negative of the feedback impedance over R sub 1, or the input resistance. And if we now substitute this z sub f expression into where z sub f is, let's pull the r1 into the numerator, we end up with minus r sub f over r1 over s r sub fc plus 1. And that's now the transfer function, this third circuit, which is a low-pass filter. What's the order of that low-pass filter? First, what's the DC gain of that transfer function? That's evaluating this transfer function at s equals 0, which you could think of as that if you wanted to, but we now replace s with 0 and we have minus r sub f over r sub 1, and that now looks similar to just the pure inverter circuit, and that's what happens to DC frequency or constant inputs. But we bought a little bit more than that kind of behavior or response because of the insertion of that capacitor in the feedback path. We now have a pole in this transfer function, and where is that pole? Or by definition, how would we find that pole? How are poles defined? When the denominator vanishes or equals 0. If we do that, we say, okay, we have s r sub fc plus 1 equaling 0. If I solve that for s, I now have a pole at minus 1 over r sub fc. And that now provides us with, I'm sort of giving you information that we will learn a little bit better after today or in the future. Our break frequency, or where we sort of switch from being a constant magnitude to where one that's rolling off, that's this break frequency, and that is this pole locations value. The break frequency, we could say, is omega sub b, is this 1 over r sub f c. So that a straight line magnitude plot of the magnitude of h sub 3 of j omega as a function of frequency, we are approximating that by saying it's going to be flat. That's supposed to be a flat line. Ugh. Looks better when I just see it on the tablet. When it gets... Okay, use your imagination. That's flat. And now at this break frequency, it starts rolling off at a constant slope. It's just a first order, so it's not going to change the slope once it starts sloping. Here is our break frequency. What is the value of the magnitude of our transfer function, let's say in dB? That's now 20 times the log base 10 of the absolute value of that transfer function at, let's say, DC. And what was that? What was our DC magnitude? R sub f over r sub 1. So if r sub f was 10 times r sub 1, we now have an absolute gain of 10, which in dB, what's the log of 10? 1. The log of 1 is 0. The log of 10 is 1. The log of 100, 2. The log of 1,000, 3. Now we're counting. Doesn't this feel good? The log of 0.1, it's 1 over 10, so we could say 10 to the minus 1. We could throw that minus 1 out in front, and we have minus 20. 0.01, minus 40. Do you see how this is working? did I want to say? Oh, which means that if we are flat, somebody brought in, never mind. We are rolling off at a constant rate of minus 20 dB per decade, or, for those of you that are musically inclined, it's 6 dB per octave. Octave. What's a decade? 10 years, right? But that in this context, that means a factor of 10. If that break frequency was, let's say it was 3 radians per second, then a decade beyond 3, or a decade higher than 3, would be 10 times 3, or it would be 30. We run over to 30 in omega, and we would be at minus 20 dB. If we went to another frequency that was a decade beyond 30, which would be 300, and we looked and found the magnitude, we would then be at, we're at minus 20, we went one more decade, now we're another minus 20, we're at minus 40. How that works. Maybe you don't want to do these big stretches of a decade change in frequency. Maybe you want to go a little bit shorter before you sort of check in and say, where are we? Then you might be moving in terms of octaves, and that's now a factor of 2. Can somebody save me if I ask what's the A above middle C, frequency-wise? 440. Thank you. So now if we go an octave above that on the piano, now we would be at 880. If we went an octave below, we would be at 220. And if I could sing, you could hear those different frequencies. 220, 440, 880. And those are a change of an octave, a factor of 2. Which means that if we were sitting at our break frequency of 3, and I said, what's the dB in this straight line sketch, an octave beyond 3, what frequency are we talking about now? We were at 3, we go an octave higher, that's a factor of 2, so now we have 3 times 2, high level math, 6. So now we're at omega equal to 6, and where are we in our magnitude? Minus 6. We're down 1 octave beyond. So if we now went 3 octaves beyond 3, so we go from 3 to 6, that's 1 octave, 6 to 12, which is 2 octaves, 12 to 24, now we've gone 3 octaves. We are now at 24. In terms of frequency, where are we in terms of magnitude? Minus 6, minus 12, minus 18. We're now minus 18, and where were we at 30? A decade beyond 3, we were at minus 20. So now, doesn't that make sense? Isn't that consistent with our line, our slope? At 24, we're at 18 minus, and at 30, what did I just say? When we were at 24, we were at minus 18, and when we were at omega equal to 30, we were at minus 20. Is that better? Is that correct? Is that making sense? No? So just remember, octaves are factors of 2, and decades are factors of 10. And if somebody says, oh, I want I want you to build me a low-pass filter with a cutoff frequency or a break frequency of 1200 hertz. And I want the magnitude at 2000 hertz to be down minus 55 dB. That's going to tell you how to design your filter. You're going to be needing to know those particular ways of thinking about that, those specifications. Yes? Yes. Oh, thank you. So the minus 20 dB is relative to where you're starting. So there maybe I should have said that R sub F and R sub 1, let's say that they were exactly the same resistor. Then where would I have been starting? 0 dB. Then I would be always going down. If it just so happened that R sub F was 10 times R sub 1, then we would be starting at 20 dB, and then a decade beyond the break, we would be at 0 dB. We would be minus 20 from 20. Using too many round numbers. Yes? Where did the 20 come from? So now if you look at this formula, where did the 20 come from? 20 log of something. If you now look at that and you say, okay, what's going to happen if I go from, let's just say that that starts at 1, the argument of that log, so we're now at 0. Now if we advance that, that argument inside that log expression is usually a function of frequency. So that now if we say, let's go a decade further out, so that now we are actually looking at, let's say, 1 over 10. Now we have minus 20. Oh, where did the 20 log whatever come from? That's coming from, if you look at, that's how we define dB. dB is 20 log of a magnitude. And it's really coming, if you just looked at maybe powers, you would have 10 log of something. So now the something is usually in terms of voltages. This is now just the formula for magnitude in dB. It's 20 log of this transfer function's magnitude. All right, that's circuit 3. Let's look at another circuit. Let's call this 4. I know this is really 3 to 4. That kind of makes sense, I hope. Let's look now at a high-pass filter. And let's use an active device, which means that we are building around this op-amp. Suppose that I now have, going into the inverting terminal, let me call this R sub F, and this, let's say, is R sub 2. And let's now take that to ground. There's a good. But now into the non-inverting terminal, now you're going to like this because there, we switched away from capacitors. Now I gave you an inductor. So now I have this inductor going to ground, and I have my source, call that V sub G, on the other side of that resistor. And that resistor, let me call that R sub 1. And did you analyze this circuit in 220? I don't know if you did or not. It doesn't matter. Let's figure out how to analyze it. I'm just carrying on a conversation. Let's call this point right here, let's call that V sub P. And I'm going to call that current there I sub P. And let me call this V sub N. And I will call this I sub n. First, is this going, yes, question? What does active mean? Active means it's powered. It's different from passive. So a passive means we have resistors, inductors, and capacitors, typically. So now active means that we have a device that we have to energize to make it active. If we didn't power that op amp, it wouldn't do anything. So we have to energize it. We don't even show you that, but it's connected to a supply, and the fact that it's now energized allows it to behave very nicely so that we can pack around it some passive components that make it sing in the frequency behavior that we want. And what we want to do now is see how does this particular device behave when it's interconnected with these R's and L's. So active just means, in this class, it's going to mean you have an op-amp-based circuit. You now have energized devices that need to be powered up before any of this is going to work the way you expect it to work. All right. Now, how are we going to do this? First, is it going to give us a well-behaved, is it going to be well-behaved as a circuit? And what do we mean, or what do we need it to, what are we meaning by well-behaved? Yes? Why is it a high-pass filter? I haven't told you that. That's what we're going to try to derive. So I just gave you the title. That's basically a clue saying, oh, this must, he's saying this is high-pass. Let's verify that. Let's see how that description is appropriate for this circuit. And what do we need these op-amp circuits usually to be? How do we have them configured for them to play nicely? We need negative feedback. Does this have negative feedback? Yes, it does, because we are actually feeding back this output waveform into our inverting terminal. That's now giving us the negative feedback. So this is going to behave the way that we want, meaning now we know that V sub P and V sub N, the voltage drop across those two is negligible. What else do we know about I sub N and I sub P? Those are going to be zero. This is not absorbing any current or asking for any current into those two input terminals. It's getting everything it needs from the power supply, which we haven't even shown, but it's connected to. Let's look at, for starters, let's look at this piece. If I do not have any current going into I sub P, do you see that that little piece is sort of isolated in effect? I can just analyze it by itself. That's what I want to do now. Let me say, let's examine. I'll call it the V sub P subcircuit. And we can make that a subcircuit because I sub P is equal to 0. Now we can simply if we wanted to re-sketch that piece or that subcircuit, here is V sub G, here is R sub 1, and here is SL, and we now want to know that's really the V sub P in our circuit. That's the voltage of that non-inverting terminal relative to these triangles that are representing our ground. in this circuit. How do we find V sub P in terms of, and V sub G is just our supply. That's a voltage divider. If we now look at this as a voltage divider, we now have V sub P of S is equal to SL over R1 plus SL. And that now scales the input V sub G of S. That's not really in any of the structures or forms that we want. It's not really in pole zero form because S, its coefficient hasn't been normalized to 1, and it's not really in time constant form because the constant in the denominator hasn't been normalized to 1. This is sort of in between those. So let's put it into one or the other of those forms so that we can maybe get a better feel for what's going on. Suppose that I factor R sub 1 out of the denominator. I now have SL, I now have R1, I have S times L over R1 plus 1. There's the 1 that I wanted in my denominator expression. And I can now write that. If I put the R1 in the numerator, I now have S times L over R1. That's just a number. And now I have S, L over R1 plus 1. What's my time constant? It's all of that that's multiplying or scaling S. This is now my time constant. That's L over R. Let's say that's tau sub 4. And this particular representation for that transfer function we could have had a picnic. I think that had a lunch in it. I could smell something. It was pretty tasty. Sorry if you're hungry. I apologize. But that's now in time constant form. If you're listening to this lecture, you have no clue what I'm talking about. That'll teach you. You need to show up for class. Question? No. So the question, that's a good question. Does the S in the numerator have to be multiplied by the same tau? No, it doesn't. We are just looking for time constants in our denominator expression, and in this case it's nice or easier because it's first order. If it's second order, then we have to do this for each of these pieces, or if it's third order. But here it's first order, and it's pretty easy to find the time constant in that. But the fact that the numerator has an S in it, the fact that that S is actually scaled by the same formula is irrelevant to the time constant in that form. So that's our time constant form. We could also, if we wanted to, rewrite this. Let's say that we had it in this form, and I wanted to get it in pole zero form. Now what am I wanting to do? I want to get that L away from S. I want to factor around. I want to make the coefficient of my S equal to 1. If I do that, suppose that now I take this, so this was the time constant form. What if I now say that I could also rewrite that? If I factored out the L from the denominator, do you see that I have an L in the numerator and they will cancel? And I now have an S plus R1 over L, and up here I have an S. And that's now still the V sub G. And that's really the reciprocal of my time constant, and that's where the pole is at negative that value. Here is V sub P of S. And let me call this, let me call this H sub P of S, because this isn't the total transfer function of that circuit. Now it's just the subcircuit between the input and that non-inverting terminal of my op-amp. This is the pole zero form. But can you give me a picture as to what this is doing with respect to frequency? What happens at high frequencies? It goes to 1, doesn't it? The denominator, that if S is really, really big, the R1 over L will be dominated by the S, and that will be very close to the S in the numerator, and this is going to go to 1 for high frequencies. What happens at low frequencies? What happens at a really low frequency? At DC. It goes to 0. So now we're going from DC at 0 up to a level value or a value of 1 at high frequencies. So we're attenuating low frequencies and we're passing higher frequencies. This is a high pass behavior. And if we wanted to sketch this, that S in the numerator actually says in a dB scale, the reason we're doing dB is because now we have all these straight lines. We never get to 0. That just keeps going to more and more negative dB. Minus 20 dB, minus 40, minus 60, minus 80. Gets really, really small, but we never get to 0 on a logarithmic scale or in a dB scale. Then we will break. And this break will be where the pole is. And the pole is now at a frequency of R1 over L. And how fast, since this is coming up from the bottom, from the basement, because of that S in the numerator, how fast do you think this is coming up? 20 dB per decade. All of these first order factors give rise to this 20 dB per decade slope. And we're going to deal more with that later. I'm just sort of giving you this picture now. But that's not the complete analysis. We now need to figure out how does this additional circuitry connected to this op-amp impact that frequency-dependent piece that's connected to the non-inverting terminal. Suppose that I now write a KCL at that inverting terminal node. I'm now going to look at this guy and say, can I write a KCL equation at that terminal? Meaning, if I now say, let's do a KCL at V sub n, V sub n is one of my a voltage. If I now said, what's the current leaving that node and going to the left through R sub 2, how would I write that current? It's the voltage dropped across R2, which is V sub n on the right minus 0 on the left, divided by R sub 2. That's the current going to the left. I now can say that's Vn minus 0 over R sub 2. What's going into the inverting terminal? What's going right horizontally? Nothing. So we have plus 0. And now what's going current through R sub F going from left to right? How would I denote that current or describe that current? What was the R sub F? Is it clear where those expressions are coming from? That's just KCL at that inverting node. If I now combine my terms that are associated with V sub n and V sub o, I now have 1 over R sub 2 plus 1 over R sub f times V sub n, and that's equal to V sub o over R sub f. If I solve that for V sub o, or just multiply both sides by R sub f, I now have an R sub f over R sub 2, an R sub f over R sub f, which is 1, times V sub n. And let me call this transfer function h sub n of s. Which now I can say that V sub 0 of s is h sub n of s, V sub n of s. But how do I know, is there a relationship between V sub n and V sub p in this circuit? Because of negative feedback, those are essentially the same voltage. I can now rewrite this and say this is V sub n of s times V sub p of s. But I already have a formula for V sub p in terms of the real input, which is V sub g. I can now say this is h sub n of s. V sub p was h sub p of s times V sub g of s. And this combination of those two transfer functions I will now call my total transfer function between the source, V sub g, and the output of that op-amp, V sub o. That's now h sub 4 of s. Or, if I combine those, I now have s times R sub f over R sub 2 plus 1 over s plus R sub 1 over L. And that's now my h sub 4 of s. At high frequencies, where is that going? Do you see how this compares, this h sub 4 compares with h sub p? The denominator is exactly the same. All I've done is changed the numerator by this scaling factor, R sub f over R sub 2 plus 1. So this should be shaped just like this. And where's my break frequency? That's now this R1 over L. How fast am I going up? That's 20 dB per decade, or 6 dB per octave. Just that this flat, high-frequency passband gain is different than it was in the earlier circuit, or the sub-circuit. Now it's going to be a function of R sub f over R sub 2 plus 1. You now, I hope, have seen where you could generate low-pass behavior from a circuit, and that's a fairly basic circuit. You could generate a high-pass circuit, from something like that. And if you start combining these in various ways, you can actually generate, if you said, oh, let me do high pass for a while and then at really high frequencies, let me kick that down and do a low pass, what kind of a filter shape is this? This is a band pass. And if you said, oh, what if I now do a low pass and then I do some high passes? That one called. Have a lot of bands floating around today. This is a band reject or a notch filter, depending on what you want, how you want to refer to it. Meaning, you can now start designing low pass, high pass, and band reject filters. Active filters. Active because op amps. Now, let's talk. Sometimes you just want to be playing without building circuits. You want to just say, how can I start creating some behavior? Let me do this on the back of an envelope before I start going and bothering Josie to get some parts. I want to know what can I do before I start trying to build this. Let's now look at what's possible or how we might be thinking about response of a system or systems, and a way to conceptualize these might be with respect to poles and zeros in the S-plane or S-plane diagrams. I will try to be on the left will be my time domain, and on the right will be the frequency or S domain. And as electrical and computer engineers, you need to be comfortable going back and forth, thinking in both. Suppose that now I looked at a passive low-pass filter. If I said, what's the transfer function? What is a transfer function for a passive low-pass filter? Could you just throw one at me? We derived one to be 1 over RC over S plus 1 over RC. Now so that's in the frequency domain where we're talking, what does this look like as a function of frequency? At low frequencies, it's 1. At high frequencies, it starts rolling off. Now somebody might say, well, what's the impulse response of that low-pass filter? What does that look like? So now we have to move back into the time domain. What is h sub 1 of t? Now you just have to inverse Laplace transform that. What kind of shape or mode will you see in the time domain? This, if you just erased the numerator and said, I can't deal with that, I need to just look at what I see in the table, maybe you have 1 over S plus A. You now know what A is. That's 1 over RC, but that would be this e to the minus AT. We don't quite have an A over there, so let's write it the way we do, and we're actually scaling it. That's what the numerator does. That just is scaling the whole answer. That's the that's the 1 over RC. And then we have an e to the minus. A is 1 over RC times t. And we could write that many different ways. We could say this is now e to the minus t over RC, which is If you were always thinking in terms of time constants, you might say, oh, that's e to the minus t over tau, where tau is RC. Suppose that somebody says, oh, let's go back over into the frequency domain now that I kind of have a picture of the filter in the frequency domain and its impulse response. And what's the impulse response telling us? What is that? What is H sub 1 of t? This is a low-pass filter. How would we get that behavior out of it? Oh, and maybe... when would we see this? Or how would we see this? If somebody said, can you create the impulse response in the lab for this circuit? What would you need to do? Excite it. And what are you going to excite it with? It's the impulse response. It's being excited by an impulse. You have to hit this circuit, this low-pass filter, with an impulse. Right? And then you see what? What does this do? What's it do at 0? At time t equals 0, where is it? 1 over RC. At one time constant, what is it? When t is equal to tau, it's e to the minus 1. And what's e to the minus 1? 0.37. It's about 37% of where you started. At 2 time constants, it's 0.37 times 0.37, or e to the minus 2. And by the time you get to 5 time constant, where are you? 1% of where you started. You're less than 0.01 times 1 over RC. This is just going down. This is an exponential. When you hit it with an impulse, that's your low-pass filter. And, well, let's put some numbers in. Now somebody says, oh, I've gone to Josie, and I have now figured out that I want 1 over RC to be 10. Where's your pole in this filter? Minus 10 what? What are the units? Radians per second. And you could relate that to frequency in hertz by this 2 pi factor. 2 pi f is omega. Now, if this is what capital H sub 1 is, what is lowercase h sub 1 of t? If 1 over RC now is 10, this is now 10 e to the minus 10t, t greater than or equal to 0. Our RC, 1 over RC was 10. RC, since we were dividing, is 0.1. So our time constant is 1/10 of a second. What's that look like? If you now had to sketch that, where are we starting? If this is H sub 1, and you could graph this on your calculator if you couldn't graph it by hand, but I think you can graph this one by hand. Where are we starting? At 0. That's at 10. And when are we going to be done? 5 time constants, and what is our time constant? 0.1. So now in 1/2 of a second, we are finished. So these scales are not the same, but by the time we get to 0.5, we are 1% of 10. We're at 0.1. What's the diagram in the frequency domain look like? What's our pole 0 diagram or the S-plane plot look like? Here is the imaginary value of S. Here's the real value of S. Do we have any open circles? Do we have any finite zeros? No. How many poles do we have? One, and where is it? That's the pole zero diagram that produces that impulse response. What if now somebody says, okay, there's my system, that's my low pass filter, it's passive. What if they now say, I'm going to give you an input, and that input x of t, let me say that's e to the minus 2t for non-negative values of time, or I'm switching it on at time 0, and that means I can multiply it by u of t. What's that look like as a function of time? Maybe I sketched my earlier one. Where do I begin? What's the value of x at 0? 1. When do I finish? What's my time constant? What value does t need to assume to make 2t equal 1? So now I set 2t equal to 1 to find my time constant, and what's t? 1/2. So now how long do I have to wait before I no longer see this exponential decay? 5 of those, 5 times 1/2, so I'm now 2.5. So my time up above was a little bit, let's say, too big for me to fit it on this page. Let's say this is now 1/2, and now this is 2.5. I now have this exponential. And where am I? And this isn't a very good exponential decay, because where should I be at 0.5? One time constant into this response. E to the minus 1 times 1, and I said e to the minus 1 was 0.37. So that should be at about 37, or 0.37, 37% of 1. And I don't think it is. So you can improve your sketch. And at 1, it would be at e to the minus 2. At 1.5, it would be at e to the minus 3. 3 time constants. What's the S-plane plot of this input look like? If you now Laplace transformed little x of t and generated capital X of S, what would you find? That's now 1 over S plus 2, so that now you have a pole due to your input at minus 2. If you now are applying that input to this low-pass filter to create the output, now what do we have? Well, here's where you probably want to play in the frequency domain. You go, I've had enough of homework 7, let me do some algebra in the S domain, let me just find the output Y of S. What's that equal to if I have a system and an input and I know both of their transforms? Multiplication in the frequency domain. And what does this pole zero diagram look like now for this particular choice of X and H? Here's the S-plane. Y of S. What was H? Thanks to Josie, it's 10 over S plus 10. What's X? We just said that that was a decaying exponential with an exponential of minus 2. There is now Y. Where are my poles and zeros? I now have poles and zeros, 2 poles, no zeros. One of those poles is due to my system, another pole is due to my input, and they're together now in the output. In the time domain, what's the expression formula for y? It's convolution, which you could quickly write by a star, right? You can say h star x. I'm convolving x with h. And you should be able to do that on the exam. If I give you an exponential for h, give you an exponential for x, you better be able to convolve those and show me all of the steps in that process. But here, if I don't tell you which way I need you to solve that, how would you maybe prefer to do that? Can you inverse Laplace transform capital Y of S? What does that look like? Or what do you want to do if you now have this collection of pole factors in your expression for capital Y of S? Partial fraction expansion. You have 2 factors. You have a factor S plus 2 and you have a factor S plus 10. And you can find those 2 numerators. The numerator, or the partial fraction expansion coefficient, over the 2, or the S plus 2 factor. You multiply Y of S by S plus 2 and evaluate at S equal to minus 2. So now we have 10 over minus 2 plus 10, or 10 over 8. Five over 4, 1 1/4. So we have a $1 1/4 for our gain. Maybe you can buy a lottery ticket, I don't know. $1 1/4. What's the other gain? Now we multiply by S plus 10 and evaluate it at S equal to minus 10, and we now have 10 over minus 10 plus 2, or 10 over minus 8. What's this look like in the time domain? Does everybody see that? You now have a low-pass filter, and you've excited that low-pass filter with a decaying exponential. The filter was, in terms of its speed of response, was it faster or slower to respond than the input that you applied to it? The filter had an impulse response that looked like this. It was done after half a second. Your input, relatively speaking, is done after what? 2.5 seconds. Which one is faster responding? The low-pass filter, isn't it? What's this going to look like? Do you see what this looks like as a function of time? What would you do on an exam or on an interview and somebody said, "Oh, you've analyzed that beautifully. Can you tell me what that looks like in the time domain?" Exponentials, linearly combined? Yes. But what you might do is you might say, you know what? Which of these is going to dominate? Which of these exponentials? Which one's the slowest one? What would happen if I sketched that? 1 1/4 e to the minus 2t. Could you sketch that? you would know that you're starting up here, let's say at 1.25, and where do you finish? At 2.5. So that now you could say, oh, if I neglected that piece at minus e to the minus 10t, this is what I would see. But what does the e to the minus 10t look like? That was just that, wasn't it? Except now we're subtracting it, so that now we have this. Do I have enough going on here? Oh, oh. So what happens if I combine numerically that black and blue? You're all bruised. But do you see what you can do? At 0, what am I? At time t equals 0. If you plugged in time t equals 0 to this, you have 1 minus 1 scaled by 1 1/4, or 0. So you're starting there, and that makes sense with your blue and black. And what's going to happen? Well, the e to the minus 2t is not disappearing as quickly as the e to the minus 10, but do you see that you're sort of doing this? And now you've sketched the response to that curve without needing a calculator. You've now just sketched it. And what is this response of? What have we done? You've low-pass filtered an exponential, and that's what this red curve indicates. That's a low-pass filtered exponential. When you really were applying, what were you applying to the system to begin with? That was the excitation. That's how you were exciting the system, not with an impulse, but with a decaying exponential. And this is what was generated as an output from that low-pass filter. What if we excited that system, or applied not an exponential, but what if x of t was a cosine omega naught t? What if I said, well, what's going to happen, or what does the pole zero diagram look like in the S-plane when I have h of this low-pass filter and this input x? Where does the h come into play? Or what does that produce in this complex S-plane? Your low-pass filter, what is that? How do you represent that in this S-plane? Really? How did we represent it before? It hasn't changed. It's still a low-pass filter with a bandwidth of 10 radians per second. It's now producing or giving rise to this pole at minus 10. Does everybody see that? If we applied a complex, or if we applied an exponential, this is what happened to our S-plane. Now we want to apply a sinusoid, a cosine of omega naught. What's that look like in the S-domain? Now if you put that into a Laplace transform, that you would have S over S squared plus omega naught squared, would you not? So that now you have that. What's going to result from this picture? What's going to happen in the time domain? Now you are shaking this low-pass filter at omega naught. It's going forever, isn't it? It's painful. It's painful. It just keeps going and going. Because why? Those poles are where? Right on the imagine. There's no decay. There's no exponential decay. It just keeps shaking. So what would you think you would see at the output? I just keep shaking this system. What do you think you're going to see at the output? The same shaking, right? That's the only thing it can do. What you may have is a transient. You will have a transient due to that pole at minus 10, but eventually your system is just going to keep shaking. We'll figure out what it does with that shaking on Thursday.